Cavendish Laboratory at Cambridge University, where the constituents of the atom were first discovered, the realm of the very small. From the time of Democritus in the 5th century BC, people have speculated about the existence of atoms. For the last few hundred years, there have been persuasive but indirect arguments that all matter is made of atoms. But only in our time have we actually been able to see them. Here, the red blobs are the random throbbing motions of uranium atoms, magnified 100 million times. How Democritus of Abdera would have enjoyed this movie. We pretty much take atoms for granted. And yet, there are so many different kinds, lovely and useful at the same time. Look. There are some 92 chemically distinct kinds of atoms naturally found on Earth. They're called the chemical elements. Virtually everything we see and know, all the beauty of the natural world, is made of these few kinds of atoms arranged in harmonious chemical patterns. Here we've represented all 92 of them. At room temperature, many of them are solids, a few are gases, and 2 of them, bromine and mercury, are liquids. They're arranged in order of complexity. Hydrogen, the simplest element, is element number 1, and uranium, the most complex, is element 92. Some elements are very familiar. For example, silicon, oxygen, magnesium, aluminum, iron, the elements that make up the Earth. Or hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, the elements that are essential for life. Other elements are spectacularly unfamiliar. For example, hafnium, erbium, diprosium, praseodymium, elements we're not in the habit of bumping into in everyday life. By and large, the more familiar an element is, the more abundant it is. There's a great deal of iron on the Earth, not all that much yttrium. The fact that atoms are composed of only 3 kinds of elementary particles, protons, neutrons, and electrons, is a comparatively recent finding. The neutron was not discovered until 1932, and it, like the electron and the proton, were discovered here at Cambridge University. Modern physics and chemistry have reduced the complexity of the sensible world to an astonishing simplicity. 3 units put together in different patterns make essentially everything. A neutron is electrically neutral, as its name suggests. A proton has a positive electrical charge, and an electron an equal negative electrical charge. Since every atom is electrically neutral, the number of protons in the nucleus must equal the number of electrons far away in the electron cloud. The protons and neutrons together make up the nucleus of the atom. Now, the chemistry of an atom, the nature of a chemical element, depends only on the number of electrons, which equals the number of protons, which is called the atomic number. Chemistry is just numbers, an idea which would have appealed to Pythagoras. If you're an atom and you have just one proton, you're hydrogen. 2 protons, helium, 3 lithium, 4 beryllium, 5 protons, boron, 6 carbon, 7 nitrogen, 8 oxygen, and so on, all the way to 92 protons, in which case your name is uranium. Protons have positive electrical charges, but like charges repel each other. So why does the nucleus hold together? Why don't the electrical repulsion of the protons make the nucleus fly to pieces? Because there's another force in nature, not electricity, not gravity, the nuclear force. We can think of it as short-range hooks which start working when protons or neutrons are brought very close together. The nuclear force can overcome the electrical repulsion of the protons. Since the neutrons exert nuclear forces, but not electrical forces, they are a kind of glue which holds the atomic nucleus together. A lump of 2 protons and 2 neutrons is the nucleus of a helium atom, and it's very stable. 3 helium nuclei stuck together by nuclear forces makes carbon. 4 helium nuclei makes oxygen. There's no difference between 4 helium nuclei stuck together by nuclear forces and the oxygen nucleus. They're the same thing. 5 helium nuclei makes neon, 6 makes magnesium, 7 makes silicon, 8 makes sulfur, and so on, increasing the atomic numbers by 2 and always making some familiar element. Every time we add or subtract 1 proton and enough neutrons to keep the nucleus together, we make a new chemical element. Consider mercury. If we subtract 1 proton from mercury and 3 neutrons, we convert it into gold, the dream of the ancient alchemists. Beyond element 92, beyond uranium, there are other elements. They don't occur naturally on the Earth. They're synthesized by human beings and fall to pieces pretty rapidly. One of them, element 94, is called plutonium and is one of the most toxic substances known. Where do the naturally occurring chemical elements come from? Perhaps a